Hello everyone, welcome to my YouTube channel. Today we are going to talk about the exercise. We'll discuss about hard margin SVM exercise problem. If you guys like this video, if you want me to do a theory part on hard margin SVM and soft margin SVM, do let me know in the comment section. Let's start with the question. The question is very easy. It just looks intimidating, but trust me, it's very easy. It's so simple. Don't just don't get terrified. Let's start with the question. Interestingly, the linear hard margin SVM given by this is the hard margin SVM problem, and this says that it requires only two non-equal training points with opposite labels to find a separating hyperplane. Let x be some endpoints, y be n labels, x belongs to Rd, and y have the labels -1 and 1. This be a data set. We have the optimal solution, that is, we have an optimal margin, optimal W, and optimal B. And they say that assume W1 is not equals to 0, because later on when we will need the value of the W, if it's 0, we cannot find the other value. Okay, just leave it here. I'll explain you later on when I'm doing the solution. And they say, okay, the question says that they have a problem, that is equation 1. They have got the optimal solution, that is this. Okay, there's the problem, this is the solution. That's it. Simple. What you have to do is you have to find 2 points that have the same solution as this. This is it. You have to find 2 points that has same solution as this problem has, and that is this solution. You should have optimized margin. Your 2 points should have optimized W star and B star. Okay, so now the issue is that how you're going to find the 2 points that have the same solution as the above problem. Now, this is not actually an issue. We'll make it easy. How we can make it easy is that it's simple. You have got the optimized solution. You have got optimized W. You have got optimized B star. From here, by using this, you can get the equation of optimized hyperplane. Okay, this problem has an optimized hyperplane. So first you'll try to get the equation of optimized hyperplane by using these. Okay, and then what you will do is I'll show you. Okay, it looks, oh my god, a lot of stuff, a lot of stars. Oh my god, it's so difficult. No, it's not. It's really easy. I'll just explain it to you, and then by the end of the video, you'll be like, oh, it's so easy. Okay, let's start. Now, I told you that you have an optimized hyperplane from the question, okay, from equation 1. Just remember this equation 1. I'm going to talk about this equation whole time in my rest of the video, okay? This equation 1, this has an optimized solution. This has an optimized solution, that is optimized margin, optimized W star, optimized B star. Okay, so now what we are going to do is from that we are using W star and B star, and we will find the equation of the hyperplane. We assume that W1 star is not equals to 0. I told you I'll tell you later on. Now it's time. W1 is not equals to 0, as when we will solve the equation of the hyperplane, when we put W1, the first value of the W vector, when we put it in here, it shouldn't be equal to 0, because if it's 0, we cannot find the x1 value. Okay, so that's why we are specifying that W1 is not equals to 0. Just assume that. Okay, and then we are also saying that x1 belongs to R and rest of xi are 0. We are just stating this just because we want to say that we just need 1 point on the hyperplane, one optimized point on the hyperplane, well, the all the points on the hyperplane are optimized, okay? So the point is that we have to find one point on the hyperplane, and with that we can find the rest of the two points, okay? We don't need these points. If they are present or if they all are zero, not our problem. So we are specifying to just clear the concept that if they are zero, even then we'll get the solution. So this x1 shouldn't be zero, and this w1 is shouldn't be zero. Okay, so x1 has a value, but all other are zero. Or if they're not zero, we don't care. Okay, so we will put the w star and x star in the equation of hyperplane. With that, we get this point. This point. Okay, when we get this point, we are good to go. By using this point, we can add with the margin, we can subtract with the margin, and we can get these 2 points that we were asked to find. The question was that we have to find these 2 points, and these 2 points have the same solution, same optimized solution as the equation 1 in the question has. Okay, so now we have got this point. By adding and subtracting, we get x1 and x by adding and subtracting the margin, and these are the labels actually. Y1 is 1 and this is negative, and we get these 2 points. Okay, now we have also assumed that the vector w, the norm of the vector w is 1 in here. Okay, so we have assumed that this is the norm of the vector w is 1. Okay, now let's start with the rest of it. Now what we have got 2 points. Now what we have to do is that we have to prove that these 2 points have the optimized solution, as the question states that this equation, this problem has an optimized solution. We were supposed to find 2 points that has the same optimized solution as this problem. So we will prove we have found the 2 points. Now we will prove that these 2 points have same optimized solution as equation 1. Now we will do what we will do is that we will put these 2 points in equation 1. Okay, now let's put the equation 1 in parallel in here so that it'll be easy for us. This is the equation 1. We will put the value of x1, that is this, in equation 1 in here, and the b comes as it is. And one point to remember, that I have not written this in here, the complete equation, as the space was less, but at the end when we'll get this part solved, then we will compare it with this. Okay, so then we will compare it with this. We cannot, this just comes from here, from here. I hope you get it. You are smart people. Okay, so now what we do is that we are putting the value of x1 in here. First we'll solve for x1, then we'll solve for x2, and then we'll see what we have got. We have put the value of x1 in here, and then what we do is that this x is actually this one. Okay, so well, you can see that, oh my god, this is x1 and this is x, and how can we substitute this in here? Oh my god, no, it's just that I have differentiated. This x1 has this value, and then I cannot put 1 in here because these will just look same. So you can name it the way you like, but for me it was getting confused, so I just named this x, and this is x1. So I am just, this is just this the same. I can put this is x1 actually. So I in x1 I have put this, and in this x1 I'll put this value. I hope I didn't confuse you people. It's just easy. Just do it yourself. You'll get it. It's just easy. I've just substitute the value of x1 in here, and here in this xi I have substituted this x1. Okay, now what happens is that this is w star transpose, then we will multiply this inside. We will multiply W transpose star transpose with this X and then with this. Okay, so now here's a little thing to pay attention. This is actually X1. Okay, so this is just one value, out the first value, or just one value of the entire X, entire capital X. Okay, so we will multiply it with the one value of the W vector. Okay, the first value of the W vector will be multiplied with the first value of the X. Okay, so that's why we are not multiplying the whole vector with the x1. We are multiplying the first value of the vector with x1. But here there is whole vector, so the whole vector, sorry, here is the whole vector, so whole vector gets multiplied with the whole vector transpose. And now how we get this W norm square? How do we get this? We get this from here. As we have not assumed this. This is actually maths. W norm is equals to W transpose W. So as we don't have, when we multiply W transpose W in here, we don't get under root. So what we do is that we square on when we square on this both sides, this square gets cancelled with this. Okay, so okay, now squaring both sides, and this square gets cancelled with this, so now this is equals to this. So when we get W transpose W in here, I have skipped actually one step, so I'm explaining it to you. So when we multiply W star with W, we get this, and we square on both sides, so this is equals to this. So we replace this with W norm whole square. Okay, then we move forward, and we have just assumed that B is equals to 1. We have assumed that B is equals to 1. Okay, so now replace B with 1. Okay, this y1, the label is 1, so we have replaced with 1, and we have replaced B with 1 also, so it, then these two gets cancelled, and this square gets cancelled with this, so we are left with this. These two also get cancelled, so this is equals to this, and this comes from the equation above, that is this. We have put the value of x1 point in this equation, we have solved it, and we have proved that this also has got the same optimized solution as this. Now we will check x2 point. For x2 point, it goes the same. We put the value of x2 in here. In this equation, we put the value of x2, and this equation gets replaced with this. And then in this x, we put this x1, because we are taking the distance from, we are taking the x2 point with the same x1 by adding the subtracting the margin. So we multiply it. W, we are not multiplying the whole W vector with x1, as this is x1. Okay, this is x1. We multiply the first value of the vector with x1, but we multiply the whole vector with this vector, as we have got a vector in here. So what we get is like this. I have explained, we get W transpose over W. When we square on both sides, we get this W norm square. We replace this, we can replace this by this. We have done this in here. These two gets cancelled, these two get cancelled. In here again, we have assumed that B is equals to 1. We replace the B with minus, not minus 1, with 1. B itself has got the minus because of the because of this. Okay, so we have replaced B with 1, and when minus 1, that is the label of minus 2, is multiplied inside, we get this. These two also get cancelled, and hence we have proved that this also has an optimized solution as the above. Okay, like this one, this is equals to this. So now, since we expect both of these vectors to be support vectors, we have assumed these two vectors to be support vectors. It made sense that the constraints are fulfilled with equality. That's it. This is the solution. And see, it's really easy. It's nothing. You just find a point on the hyperplane by using the optimized hyperplane that was given in the question. And with that, you can find the 2 points by adding and subtracting the margin. And then you can put it in the equation 1. You can put these 2 points in equation 1 and prove that your solution is as optimized as the solution of equation 1. That's it. I hope you get it. If you have any problems, you can ask me in the comment section, and don't forget to like and subscribe because that will motivate me to make more videos. And if you don't like and subscribe me, any one of you, then I'll just feel like I'm not explaining it to you very well, and then I would stop making the videos. So motivate me to make more videos, and have a good day. Bye bye.